Industrial Supervision Program. I know them as Kat and Charlie. Let me introduce Catherine Dietrich and Charles Bradford.
Good morning to our senior design presentation. My name is Catherine Dietrich. I'm an industrial supervision major.
And my name is Charles Bradford. I'm an industrial supervision major as well.
Our focus this semester has been emphasizing on our major, utilizing our business courses, our manufacturing courses, and our management courses. This is one of 4 Kawasaki robots located in the Applied Engineering Center. It is utilized in the robotics class activities to reinforce the engineering curriculum. This particular robot has 6 axes.
Along with these 6 axes, each one has a specific range of motion. Joint 1 acts as a shoulder joint, joints 2, 3, and 5 acts as an elbow, and 4 and 6 acts as a wrist.
In a classroom setting, there's a probability for error. The probability for error is most likely a typical crash. When a robot crashes, the end of arm tooling jams into the workstation, causing the robot to become immobilized, and the joints freeze up.
The joints freeze up because located within each joint is an indexing ring and a sensor for position of the motor. This is because they lock up because they're not coming into alignment, causing the robot to go into a fail-safe mode, which in return locks up the entire robot. So currently the only way to recover a robot from a crash is to unbolt the robot, either spin it 180 degrees and mount it where it hangs off the back side of the workstation, and then use the teach pendant to recover the robot from a crash, or to try to basically manhandle a robot while another user uses the teach pendant to position the robot in a recovery-free crash position. So, being that this is very unsafe and it can cause damage to the robot itself or bodily harm to the user, because this robot weighs approximately 50 to 60 pounds, we decided we would like to implement a brake release controller. What is a brake release controller? It is an external device that allows the user to select any joint they would like to release the brake and manually move the robot in a crash-free position.
Our plan of action for this was to contact Kawasaki for a circuit diagram to figure out internally where the joints are, and then also to research the best option, whether that was to buy commercially from Kawasaki for a brake release controller or to design, build, and implement our own controller.
With researching our robot controller, I was able to determine that our robot controller had an external brake release port, as seen here using a 9-pin connector. Unlike other robots and controllers that have an internal brake release controller.
This right here is the circuit diagram given to us by our client. In a close-up version of it, you can see that there are 9 joints for the brake release and 1 brake release enable. And this is incorrect to our robot that is in the AEC right now because there is 6 axes. So there's an additional joint to this, which is meant for additional arm tooling.
So we contacted Kawasaki again, and this is the actual version that they sent us, which is very hard to read. But after studying, we was able to get all the valid information that we needed from this. This shows the correct number of joints and the 2 additional brakes for end-of-arm tooling. And this also gave us all of our pin locations on our 9-pin connectors located on the controller.
So this is a typical commercial brake release controller, and as you can see, it's very bulky. You would need a 2-handed use operation. You can see all the individual buttons for all the brake release and the enable buttons. So contacting Kawasaki, we asked for a quote. They quoted us $982 for their specific brake release controller. This controller allowed multi-axis use, and it did not, with that, we decided to streamline the design requirements from our client so that it could be useful in the classroom setting.
We spent a lot of time developing our own design requirements because this is an educational type of setting and not an industrial setting. We only wanted one brake to be released at a time just for safety standards. Also that all the input devices on the controller itself, either be push buttons, selector switches, anything like that to be protected for being damaged from them. Also the end product must be industrial robust. Also be user-friendly, a very simple design.
This is the layout for our first proposal, and it was simulated to a commercial controller. You can see that it would require two-handed use. It had individual brake selector buttons and individual brake release buttons, not ideal for the design requirements that our client requested. So reviewing this design, you can see that it was not meant for a single axis like they wanted. It was a two-handed operation, but it was industrially robust, and it had shielded input devices for the protection, and also the materials quoted for this proposal was at $270. So revising and streamlining down and focusing on our requirements, we needed a single axis use. We needed a one-handed operation so that the controller could be compact. We decided that the axis selection should be made with a multi-position selector switch and also a single push button.
So with this information, we came up with our second proposal, as seen here in our layout. With this, we implemented the selector switch and was able to come down to a single push button. This also was able to overall decrease the size, making a very user-friendly and compact design. This proposal met all the required design requirements that we set forth between us and our client. There's a single axis use, one-handed operation. All the axes would be selected as a selector switch with a single push button and be very user-friendly. After determining the layout, we was able to start constructing our circuit diagram. With this, we was able to identify all components that we would need to start to build our final product. At first, we selected a 12-position selector switch. Even though this had way more positions than what we needed, we decided to leave our first position as a neutral position just for safety reasons. And also, we could also expand our controller to increase or include the 2 additional brakes for end-of-arm tooling. For the push button, we opted with a momentary on-off, normally open contact. This was also for safety reasons as well. This way, when the user is using the controller, if something was to happen, they could simply depress the button and the brake would be engaged. Also, then we would just have to select a very robust 9-pin male connector that would match up to the robot controller itself.
So this is our first prototype of the release controller. It was a single axis use, a one-handed operation that you can hold in one hand. Selector switch was utilized with a push button, but it was not, however, industrially robust. So we had to redesign this by taking the pre-built 30-gauge wire and upgrading it to a 22-gauge wire. And we also upgraded the connector hardware, as you can see right there.
This here is our final build of our second prototype, as you see with our new cable and connector. Changing out the cable was not necessarily because of current issues or voltage issues. This was more because of the flexibility being used in an educational setting. Ideally, we would go around, this should be a dust collector. This is not something that really should be used unless it is a mess up in the programming itself of the robot. Lastly, we introduced some yellow heat shrink tubing just to reduce trip hazards. So with this prototype, we determined this was our best option. It met all demands with the lowest price, and between the first 2 proposals would have the lowest labor content. As seen here in this video we're about to play, our device is very simple to use. You don't have to change any of the settings on the robot or any of the motor power required settings. You simply plug it into the face of the controller, select which joint you would like to release, support the robot, press the button, move the robot to a safe, uncrashed position, then depress the button, re-engaging brakes.
So to conclude this, we met all design requirements. It is compact, easy to use, and we thought about all the probabilities of error, so we eliminated all issues of safety, and it became our best option to present to our client.
However, we would make some future recommendations. First off being that our selector switch, we did not provide enough protection to it. We was going to try to design a shield that would protect the front of the controller, but we ran out of time. Also, if you've ever been in the ADC, we have 4 robots, and there are cables and wires everywhere, so some type of cable management system needs to come into place to reduce trip hazards. Also, a way to secure the brake release controller to the workstation itself. That way, it is very lightweight, so it does not fall off of the workstation and become damaged and accidentally engage brake releases.
So after having such great success customizing a brake release controller for our client, we decided to make a make versus buy analysis, comparing our proposal 1, proposal 2, and comparing it to the commercial controller. We developed a cost model of parts plus labor, comparing that to the commercial.
As you can see here, there's a dramatic difference in pricing compared to our 3 options. With our proposal 1 and proposal 2 pricing, these do include estimated labor content. So coming in for our proposal 1 was $285. Our second proposal of $123 was buying commercially of $982. So you can see here, our proposal came in at the best option for our school.
Investigating further for our market for this controller, we identified the large cost difference and the opportunity. We set up a strategy by setting a conservative goal to sell to the percentage of this market. We developed a manufacturing plan, we developed a cost model, and analyzed the potential revenue, and from there we're going to form the conclusion to whether or not we should pursue this or not. We investigated using the reputable Robotics Industries Association. Data showed that in 2014, over 27,000 robots were sold in North America, increasing from the previous years. So we assumed market viability. We set a 2% conservative goal, which would equal selling 554 controller units. A moderate 5% goal in the market would be 1,384 units, and an aggressive 8% goal in the market is 2,215 controller units sold.
So one of the steps that we took was to break down all the activities to build our controller. This included such things as measuring, drilling, stripping of wires, soldering wires, connecting these wires to our push button and our selector switch, testing all connections before we tested it on the robot, and packaging and shipping.
Analyzing the cost model, we took into account for parts cost at $108 per unit. Mind you, this is individually priced components. Labor was estimated at $15 an hour. We did not account for facility overhead because we're assuming we're in a cottage industry. And we marked it up with a gross profit of 200%, asking a retail price for $246 for this controller unit, which is definitely significantly less than the $942 that Kawasaki was asking. We also, with the cycle time analysis, we computed the capacity. So 1 hour for a controller, 8 hours a day, 5 days a week, 50 weeks in a year, you can make about 2,000 controllers in a year. This right here is the potential gross revenue, and you can see that the 2%, 5%, and 8% market share, grossing at about 69,000 at the conservative goal, 172,000 at the 5%, and 275,000 at the aggressive market. And you can see that 2 and 5% can be achieved under capacity. To conclude this analysis, we do take into consideration that if we were to pursue this, that the parts would be bought in bulk and prices would be discounted, and also the actual number of units that would be completed and sold into the market. And so further economic analysis is necessary.
If we wanted to go further past our capacity, we understand that we would have to purchase more tooling, expand our work area or work cell, hire more labor, optimize the work activities, and account for postage and shipping costs and diversifying the product line. One thing that we did not account for was a learning curve of the employees themselves as they are assembling brake release controllers. So our cycle times could increase as the user is more comfortable building the product.
We would like to thank our families for supporting our college career, and also Mr. Kevin Nelson, the Professor of Advanced Manufacturing, Mr. Dave Eller, Instructor in Engineering, Dr. Paul Cuban, Professor of Engineering, Mrs. Donna Moore, Administrative Assistant, Hutchinson's, and Kawasaki Robots.
We would like to open the floor to any questions.
All right, questions?
Thank you. Well done. What was the most challenging part of the project?
I think one of the most challenging things was just contacting Kawasaki. We didn't always get instant feedback. Sometimes it would take a week or so. So I would have to say that.
Thank you, Charlie.
Good job, guys. My question, you gave a number for robots sold in America in 2014. Was that strictly Kawasaki, or is that robots in general? And then it's kind of a two-part question. Will your unit go onto other brands of robots directly, or will there have to be modifications made to expand the market in that way?
The 27,000 was robots in general, not specifically for Kawasaki, and our model is specified for a 9-pin D-sub connector, and also future recommendations, we would diversify the product line, so I guess it could fit each robot.
Yeah. And there is multiple robots that we could apply ours to. It would be specifically some of the 6-axis Kawasaki robots.
So the selector switch, which is a really neat idea, the final prototype you had has the numbers on it. Is there any way of identifying, maybe on the thing? And I saw it on the side in one of the photographs that you have a label of what this device does, right? The brake release. So that's an important part, because if it's just sitting there, no one knows what it does. Is there any way of identifying what number 2 means when you're trying to figure out why your robot's jammed up and which one you should brake release in order to get it uncrashed?
That's really going to depend on the crash type of scenario. When it is in a scenario like that, all the brakes will be locked up, so you will have to look what position the robot is in to determine how you're going to be able to actually move it. So it's kind of an interpretation of the user and the robot.
So I guess my question is, if this is a device that, as you said, isn't supposed to get used at all, and so I've maybe never used it, maybe used it once last semester or something, and I go in there and I lock up the robot. How do I know that you number starting at the base going 1 through 6, and which one? And what if I miss one of the wrist joints and I count 1, 2, 3, 4, 5, and then I put 5 and it's the wrong one? Is there a labeling scenario that you could add to this, or is everybody that uses these robots know what motor goes where?
Yes, you should know what motor goes where, but on the robots herself, there are labels that say joint 1, 2, 3, 4, 5, and 6.
Okay, okay. So it's already there on the robot?
Yes, they were already in place before we started our project.
Okay.
Any other questions?
All right, I have one. What if the robot crashes so bad that you need more than one axis to free it? When I looked at the Kawasaki product, it looked like you could release multiple brakes. Your product, it seems like you can only do one brake. Have you thought that through?
Not really, because we did not determine with our size of robot set that we would need to be able to select more than one brake at a time. That and it is kind of a safety issue. So it really was kind of determined by us and our client, mainly by our client, that we only want one brake at a time. So you might have to fall back on unbolting the robot, as we said before.
Okay. Any other questions? Let's give them a hand.